So, hello and welcome to the sixth DP Roy Memorial Lecture Series. We started this after the demise of our very fond colleague, Professor DP Roy, who was a high energy physicist, high energy phenomenologist in the Department of Theoretical Physics. This is the lecture series was started because of the donation endowment given by his family. We have had 5 lecture series by eminent people in the last 5 or 6 years. The series consists of a public lecture like we have today, a colloquium, and a technical talk for people in the area of high energy physics. The 5 speakers who have graced this occasion so far have been Christophe Grosjean, Kate Scholberg, Rohini Godbole, Chaba Saki, and Michelangelo Mangano. And we are very happy to have Professor Matthias Neubert from MITP here today to give us this lecture. So before we start the proceedings, let me invite Professor Neubert and Professor Chengdu, our director, will come and be here on the stage. Please welcome. So Mrs. Roy, we are expecting, but she is going to be late, but we will start the proceedings. So to start with, let me first request the TIFR director to welcome you all.
Thank you. So let me add my welcome to that of Professor Digge. Welcome all of you, particularly those of you who have come from outside to TIFR. And as Professor Digge just mentioned, that this is part of a series of talks endowed by the family of Professor D.P. Roy. And, we are very grateful for this endowment because it enables us to do things which are important not just for the Institute. For the Institute, it's important for us to be able to interact with very eminent physicists, to have technical talks with them. But it's also important for us to interact with the city. And I think it's also important for us, that's an important part of our mission, to communicate and interact with the public in Mumbai, which we do on multiple fora. This is one of them. For those of you who aren't aware of the others, we also have a very long-running public talk series called Chai and Why, which runs every alternate Sunday at the Prithvi Theatre. And I think the other Sundays it runs at Ruparel College. And if there are 5 Sundays, the 5th one is an online program running out of one of the labs at TIFR. We have many other public talks also. Please do check our webpage and our social media feeds if you all are interested. So to come back to the DP Roy lecture series, we are extremely grateful for the family for having endowed this lecture series, without which all of these activities, which are truly, like I said, they enrich the Institute, but actually, I think it's fair to say that, without lectures like this Institute would not be what it is. And so, they really fulfill a core part of our mission, and we're very grateful to the Roy family for their endowment. And we're also very grateful to Professor Neubert for having agreed to accept this invitation and to have come and spend so much time with us this year. So thank you so much, and I look forward to the talk.
Thank you. I now request Professor Chengdu to welcome Professor Neubert with a bouquet of flowers and a memento mori.
Oh, thank you very, very much. Thank you so much. Thank you. Thank you.
So Professor Manoranjan Guchait, who has been with TIFR for many years, was a close collaborator of DP. I would request him to come and say a few words about the science of DP. Manoranjan.
Thank you, Amal, for inviting me to do this job. It's really my pleasure to do it. So, good afternoon, my dear friends and colleagues. I'm very happy to introduce late Professor Durga Prasad Roy, popularly known as DP in the community. At the same time, it is also very nostalgic to me at the personal level. I think several of us, I don't think now several of us, some of you are very much aware of who is Professor D.P. Roy. Professor D.P. Roy was associated with the Department of Theoretical Physics for more than 30 years. He passed away on March 17, 2017, after a very brief illness. His sudden demise left his family, many of his friends, colleagues, collaborators in a state of utter shock. He was then 76 and survived by his wife, Dr. Monica Roy, and daughter Miss Kalyani Roy, and two very nice grandchildren. DP is one of the best-known particle physicists internationally from our country. He has carried out research over a wide range of topics in particle physics. In the very beginning of his career, he worked on QCD, which we call this non-perturbative QCD, and the particle spectroscopy. Interestingly, currently this particle spectroscopy has received a lot of attention because of the several good results from the lattice and also the quite a few discovery of bound states in the LHCb experiments. In addition to that, he also later on started the working for the colliders, the new generation of colliders. In the late 80s or the early 90s, then the several colliders, already two colliders. One is a electron-positron collider, call it the LEAP. Another one is a proton-antiproton collider, Tevatron, which was running at the Fermilab, were very popular, and particle physicists started working for those colliders. And then that time planning also started for the LHC experiment. That time also another Hadron Collider experiment was in the pipeline. That is a superconducting super collider, but somehow that got cancelled. And he had concentrated on the collider phenomenology. The collider phenomenology basically, the aim is to measure the various properties of the particles which are predicted by the standard model, and also there are some reasons. There are some reasons, compelling reasons, for which we think that there is something beyond the standard model. We call the BSM physics. So in the collider, we also try to see how these BSM particles, whatever it is, can be explored. That is the job of the phenomenologist or the collider physicist, to predict or propose how, or the guide the experimentalist, how those particles can be looked for in the colliders. So DP worked in several areas in this context, namely few that top quark physics and Higgs physics, and also looking for the BSM particles. In top quark physics, I can remember still, the DP used to give a very long talk at the very pedagogical level. He just, that time we were the MSc students. We learned, he really nicely explained why the standard models will have the 3 generation and why there has to be a top quark, something like that. And later on, he also, in top quark physics, he also proposed how the leptons from the top decay at that time can be detected, how the leptons from the top decay in the messy environment can be isolated. Okay, even before the discovery of the top quark. In the Higgs physics, he did a lot of work in the Higgs physics. For example, invisible decay of the Higgs physics, even before the discovery of the Higgs boson. Charles Dick signal, he was one of the physicists who really advocated to look for the charged Higgs boson, which is a unique and unambiguous candidate to look for the BSM particles. And he also himself did a lot of work in the charged Higgs boson with his foreign collaborators for a wide range of masses of the charged Higgs for a given framework of the BSM models. And in supersymmetry, he has done also a lot of work in supersymmetric particle searches in collider, even before when supersymmetry became the popular. He is one of them who really calculated how the strong particle can be produced in the hadron collider, and he calculated the cross section, and he presented some bounds using that time whatever the data available from the Tivatron. Those are the very nice pieces of work at that time. And in supersymmetry searches, is one of the main contribution is that how to reduce the QCD background. QCD in supersymmetry particle search, the final state will have expected to have a lot of jets and some missing informations. Okay, a lot of jets may come from the QCD processes, and QCD is the main process, most dominating process for the hadron collider. Then DP suggested how the QCD backgrounds can be really reduced by selecting the angles in the transverse plane along with respect to the beam direction, which we call the azimuthal angle. Azimuthal angle between the jets, choosing certain way, he suggested how this azimuthal angle selection can help to reduce the QCD background at certain reasonable level. Even that strategy still we follow today in experimental particle physics. DP was also equally interested in astroparticle physics, namely neutrino and dark matter, and its interface with colliders. In the area of neutrino physics, he published several well-referred papers after the discovery of neutrino oscillation. For more than 3 decades, he has published more than 200 papers, including some very comprehensive review articles. Some of his works are very well referred to by experimental collaboration. In the late 90s, DP was a leading person in our country who first introduced and taught us collider phenomenology. What I just said before, a few minutes before, he really taught us how to do the collider physics, how to do the simulation that time. Nowadays, doing that type of simulation is very easy because of availability of several kind of softwares in the public domain. But that time it was not very easy. We had to do everything from scratch. He also had a great interest in the experimental high energy physics as well, which I think made him an expert in collider physics. He wrote papers with experimental groups as well. DP is also the leading person from TFR, not only from TFR, in our country, to promote the high energy physics, organizing the 2 important national level meeting. One we call the WAPE, workshop in high energy physics phenomenology. Another one is the DAE symposium. I think both were started from here, if I remember correctly. DP was very affectionate with younger people, a quality which attracted several graduate students and postdoctoral fellows to collaborate with him on easy terms. He was equally passionate about undergraduate teaching and very keen to spread science education among young students, in particular the girl students. With this inspiration, his wife, Dr. Monica Roy, and family have created an endowment for conducting this lecture series for young students. We are indeed very grateful to them for their generous support. DP was very fond of traveling and adventure. He also had a keen interest to read and learn on history, either it is of mythological or science. Last but not the least, he was a great lover of Indian classical music and dance. Maybe from this passion, DP himself instituted Kaveri Memorial Music Show in our housing campus in the memory of his late daughter, Kaveri. This show is conducted by our housing society every year. All of us, including our family members, participate either as a participant or as audience. Although I have several things to share with you, but I will not take much time. So I stop here. So let's listen this lecture from our respected speaker. Thank you very much.
Thank you, Manoranjan. Let me now invite Professor Tuhin Roy to introduce the speaker.
Okay, it's my pleasure to introduce Professor Matthias Neubert. I'll try to be brief, but as you see that it's very difficult to be brief for someone like Matthias. He's a professor in Johannes Gutenberg University, and he's the founding director of Mainz Institute of Theoretical Physics. He has written more than 300 papers, impressive not just in number, but in terms of qualities and the areas, starting from QCD to CP violation to flavor physics, to collider physics, physics beyond the standard model. Any topic that you take in particle physics, he has basically done this. Professor Neubert got his PhD from Heidelberg, then he moved to SLAC as a research associate. Then he went to CERN as a senior staff member, then went to Cornell, became the director of the theory group, became the director of the Cornell Institute of High Energy Phenomenology. Right now, as you know, as I mentioned, he's in Johannes Gutenberg University, but he's also an adjunct professor in Heidelberg and in Cornell as well. He's a member of a number of academies. He's gotten a large number of awards, but as I said, I'm going to be brief. But let me just finish this introduction with a brief story. We, as many of you know, that we have started a particular series of schools called in the advanced topics of particle physics, hosted by ICTS. And in the very first edition, we invited Matthias, and the email did not reach him somewhere. So I thought we'll not have him as the speaker. But 4 months later, then Matthias writes to me saying that, oh, I just found that email. So instead of throwing it away, he writes me back and he says, well, how can I help? It was great. I mean, we invited him. He came. He gave excellent lectures on soft collinear effective theories. So if you go to ICTS right now and you try to find those lectures, you'll find it. And you'd realize that he's a great teacher, not just an excellent physicist. And he's an excellent speaker. And he's going to talk today speak about landscapes of fundamental physics. Matthias.
Okay. Yeah, thank you very, very much, Tuhin, for the very kind introduction, to the organizers of these lectures for the invitation, and especially to the families of DP Roy for giving the endowment for these lectures. I think it's an incredible honor for me to speak here as one of the lecturers in this series. I wanted to remind you what an eminent scientist, a dedicated teacher, mentor, and highly distinguished person DP Roy was, but you heard a comprehensive summary by a previous speaker, so I'm just showing his picture here. And as I said, it's a great honor to give this lecture in his memoriam. The lecture will have 4 parts. I will introduce you, and that's the main part of the talk, to the standard model of particle physics, since it's a public lecture. If you have never heard about the standard model, you hopefully still understand that part of the lecture. I will then briefly go beyond the standard model, talk about what I call enlarging the toolbox, namely that studying microscopic physics, the fundamental laws of nature, we not only can look at the tiniest distances. We can also look at the universe at large and combine this with what we learn at particle colliders. And then the very last part, which will be very brief, I want to make the point that even though this is what we call fundamental science, so it's not applied science, it's about finding the laws of physics, this has a great benefit to society, and I'm going to illustrate this with a few examples. Can you hear me well with the microphone here? Okay, I think standing here it's more comfortable than standing behind the laptop. So let me start with the first part, talking about the standard model of particle physics. And of course, particle physics is all about understanding the fundamental interactions in nature and the fundamental constituents. This is our two goals. And the fundamental interactions are what we call the forces of nature. You all know gravitation, gravity, which means that heavy bodies attract each other. That's the reason the Earth moves around the sun and the moon moves around the Earth, and we are stuck on the Earth because it pulls on us. So that's the most familiar force to us, but that's the one I will leave out because it's actually not part of the standard model. The standard model is about the microcosm, everything that's not gravity. And here, the most familiar force to us is electromagnetism, anything related to forces between charged particles or magnetic substances. And for instance, my laser pointer here is described by the laws of electromagnetism, and also your laptops, cell phones, and so on and so forth. So these two forces is what we call long-range forces. We can experience them over long distances. The other two forces of nature are extremely short range. You can only probe them if you look deep inside the atoms. There is the so-called weak force, the weak interactions, which are responsible for radioactive decays. And then there is the strongest force of all, so-called strong interaction, which keeps the atomic nuclei together. I should say that by now there is a fifth force, which is mediated by the Higgs boson. It's usually not mentioned in this list of fundamental forces because it's extremely short range and extremely weak, but we will come back to it later in the lecture. The fundamental constituents you find by digging deeper into matter. So you start with some matter, you look under the microscope. If the microscope is very, very good, you see it's made out of crystals of atoms. The atoms themselves have an electronic shell around them and a very, very tiny nucleus in the middle. The nucleus itself is made out of protons and neutrons. And the protons and neutrons themselves are made out of what we call quarks. And you would think this just continues like that forever, but we actually have good reasons to believe that it stops here for some time. Because we think these quarks and also the electrons are actually point-like objects, and they cannot be subdivided, at least to the best of our knowledge today. I should say that whatever I will tell you in this lecture is real science. I will simplify it, of course, in order to make it approachable to you, but it's not science fiction. So when I talk about science fictions, I will let you know that we are not sure what we talk about, but here we are very sure what we talk about. Now, how do you discover quarks? You really need very powerful microscopes. So you cannot use optical light to look inside the atomic nucleus. You need microscopes, which we call particle colliders. So we accelerate particles to very, very high energy and we collide them. And in that way, we have a microscope that can really look inside the atom and inside the nucleus. At the moment, the largest such particle collider is in Geneva, on the Swiss-French border near the Lake of Geneva and the airport of Geneva. And it's this 27-kilometer long ring, 100 meters underground, in which the particles collide. And this is what it looks inside this tunnel. You basically see these tubes, which are filled with vacuum. And in these tubes, we have beams of protons running in opposite action and colliding at the places where the experiments are, that you can see here indicated. Okay, let me see that I didn't losing maybe the batteries, or but that would look okay. Yes. Okay. Now the microscopes that we have are what we call particle detectors. They're very huge, as you can see, because their goal is to measure as much as can be measured about what happens in these proton-proton collisions. And since the collisions happen at extremely large energy, a lot of final state particles are produced. And to measure them, you see you need a huge apparatus, basically cathedrals of modern physics, 44 meters long, 25 meters high. You see, just to scale to people here. And you see there's lots of things inside this apparatus, which is because we need to measure different types of particles, charged particles, which can be measured by applying electromagnetic fields, but also neutral particles for which one needs calorimeters and so on and so forth. Complicated machines. This is how it looks before. This is the Atlas detector before it was put together. So essentially you see the bare structure of this detector, which by now is filled with electronics and millions of cables for the readout of all the signals that one takes. And what happens in these particle colliders is really remarkable. You take two protons, collide them, but according to Einstein, we know that mass and energy are equivalent, the famous E equals mc square relation. So we can actually take a fraction of the mass of these protons and their kinetic energy, make freely available energy out of this, and use that energy to produce new particles, which are not inside the protons that collide, which is remarkable that this happens. And in fact, this new particle can be anything that can possibly exist or has ever existed. Everything that can exist can be produced in this collision, as long as the energy is sufficiently large to produce these particles. And in that way, people have completed the so-called standard model of particle physics. If you know the chart of the elements, this is much simpler. This has only a few fundamental constituents, but it's also not extremely simple. You see here there is overall 17 particles. We can distinguish the so-called quarks, which are the constituents of the atomic nuclei, from the leptons, which is the familiar electron, but then two other copies of the electron. What we have here is for each fundamental particle, we have two siblings, identical properties, just a bit heavier, quite a bit heavier actually. But all the properties of these heavier siblings are the same as of the original electron and the constituents of the proton and the neutron. We call these three generations of fundamental constituents. And then we have the particles in the fourth column, which mediate the forces. So in quantum physics, not only matter consists of particles, also the forces are mediated by the exchange of particles. So for instance, when I send this laser beam to the board, it actually consists of particles which we call photons. So even light consists of particles. And then here, the last entry is the infamous Higgs boson, on which I will have much to say later on. This is a list of the forces. As I said, gravity is not described by the standard model because in the micro world, it plays absolutely no role. But the weak force, the electromagnetic, and the strong force, those are the forces described by these force particles here. And actually, even though there are 17 entries in this table, if you ask, what do I need to describe the physics around us, all of chemistry, all of biology, table, the floor here, we actually need only 3 particles. So everything that's heavy copies here, heavy particles, they are very unstable. They don't exist in the universe around us. We need to produce them actually in our accelerators. And then we have the neutrinos here, which are very interesting particles, but they don't do anything. We almost cannot see them. So let me also take these three away. And then what remains is only three constituents, the electron, and then two types of quarks which form the atomic nuclei, the protons and the neutrons. And two fourth particles, the photon, which is the carrier of light, and the so-called gluon, which keeps the atomic nucleus together. So in essence, we need these 5 particles to describe everything that we see around us. There's a nice mathematical structure underlying the Standard Model. It fits on a coffee mug to a person like Professor Roy. He knows what this means. Okay, so the first line here describes the forces, the second line describes the constituents, and the last 2 lines describe the Higgs boson and the Higgs boson's interaction with the other particles. But of course, there's a lot of, you need to study a few years of physics in order to decode what's written here, but it's really like a code. We know exactly what it means. And this Standard Model is a unique marriage of quantum mechanics and Einstein's relativity. You just put quantum mechanics and relativity together, and you impose certain symmetries, and then the Standard Model follows. There's no freedom, essentially, and it's what we call a renormalizable quantum field theory, which means it can make predictions, and it can make extremely accurate predictions, and in essence, it explains everything we have ever observed in the microworld. All these particle collisions, many other experiments, not at CERN, in other labs, are described by the Standard Model. It's the most successful physical theory of all times, and it's also a pillar of fundamental science of the past century. I want to talk about the Higgs boson because it was the last particle in the Standard Model that was discovered almost 50 years after it had been predicted in July 2012. And the Higgs boson, as I will explain, plays a very special role. It's really one of its kind. And I want to share with you the excitement of finding this particle, which for a long time was believed to be impossible. There have been papers written saying, here's the Higgs boson, this is its properties, we'll never be able to measure it. And as I said, it took almost 50 years to develop the technology to do it. And this is an example of an event display of the production of a Higgs boson, probably. We collide 2 protons in the LHC. We produce a Higgs boson, which then decays into light, like my laser pointer. It decays into 2 quanta of light, 2 photons. And that light is the green lines that are indicated here in this event. Now, how exactly do you use a law? I pressed so many times before and nothing happened. Now, let me see how I can go back here. This will be faster if I do it this way. Oops. Interesting. Okay. So this is the actual discovery plots of the 2 LHC collaborations, ATLAS and CMS, they're called, of this Higgs boson discovery in the decay to 2 light quanta, to 2 photons. And how do you actually find that Higgs boson? Well, there's many ways of producing photons in these collisions. You smash things together, you get a lot of light out. But in events which have exactly 2 photons in the final state, what you can do is you can use energy momentum conservation. If you measure the energy of the 2 photons and their momenta, the directions and the speed with which they fly, and you form this particular combination of them, then if these photons come from a decay of a Higgs boson, this particular quantity needs to add up to the mass of that Higgs boson. So what you see here is a falling spectrum without any particular feature. That's all the other events that produce photons. And then at a certain point, you see a peak. And you see the same peak in the 2 experiments. That's good. It's around 125 GeV. GeV is the mass of the proton. So it's 125 times heavier than a proton. You see both experiments find the peak at the same position, and if you subtract the background, you really see a nice peak structure. Of course, you see these measurements have error bars, statistical fluctuations, but that at the time was sufficiently compelling to claim the discovery of a new particle. By now, the Higgs boson has been measured also in many other decays. A particularly nice one is the decay to 4 leptons, which is shown by the blue histogram here. And you see again that the place where this spike is located is at the same 125 GeV. Okay, and there's other decay modes. Always what you find is a resonance at that particular mass. And these are pictures for the announcement of the discovery. This is the 2 spokespersons of the 2 experiments at the time. The experiments have won a lot of prizes for this discovery. This is the Director General of CERN at the time. And this is Peter Higgs, who was in the audience and who said, I never expected this to happen in his lifetime. Again, he had to wait 48 years. And unfortunately, he passed away now a few years ago, but he lived long enough to see his particle being discovered. And of course, there was a great response in the news all over the world. And it's not only because this was the last particle to be discovered, it was because this is a completely new type of particle that was discovered, which is what I will illustrate in the next couple of slides. So first of all, what do we know now about the Higgs boson? Actually, we know a lot about the Higgs boson 10 years after its discovery, or almost 11 years, 13 years now. We know the mass, this 125, we know to better than, just 1.5 per mil. This is actually one of the best known mass of a heavy elementary particle. We know the width of this resonance, which is very, very small. It's only it's a little bit more than 1 in 100,000 compared to the mass, very, very small. But it's known with large errors, but it agrees nevertheless well with the standard model prediction. And now the key feature of the Higgs boson is that it mediates a force, but it's the only force which is sensitive to the mass of particles. So the heavier 2 particles are, the stronger they are attracted by this Higgs force. And conversely, for light particles, this Higgs force is unmeasurably tiny, which is different from all other forces. All other forces are proportional to charges of particles, and they don't care about their masses. The Higgs force doesn't care about charges, but it only cares about the mass. This is a key property, and this has been confirmed, as you can see in this plot here. So the straight line is the prediction that the force should be proportional to the square of the masses of the particles involved. And you see for all particles where the Higgs force has been measured, it falls on that line. The heaviest particles are out here, but there are lighter particles going all the way down to the muon, which is very light, and nevertheless, it falls on that line. This is in fact the only force in the standard model that distinguishes between the 3 generations. Everything else is the same for the 3 generations. This is the only force. And there's something more to the Higgs boson, and that's the so-called Higgs mechanism. Because a priori, the following perplexing statement is true, that the mathematical consistency of the standard model requires that all its particles are massless, which is in stark contradiction to what we know, because all particles, with the exception of light, have mass. But the mass really comes from a mechanism that we call spontaneous symmetry breaking. So the underlying mathematical laws are symmetric and would not allow masses, but then the symmetry is broken in a specific way, namely spontaneously, and that gives rise to the mass. And I want to explain to you what that spontaneous symmetry breaking is all about. And we start with something familiar, electromagnetism. So if we have electric fields or magnetic fields, for example, by having charges or currents in wires. These fields store potential energy. So, for instance, if you have two charges which attract each other, if you want to pull them apart, you need to do work. So there's potential energy in these fields. And the potential energy is minimal. It vanishes when the fields vanish, which is very natural, right? If you don't switch on a current, the energy is minimal. If you don't switch on the magnet, the energy is minimal. Not so for the Higgs field. For the Higgs field, it turns out the potential energy is minimized for a non-zero field value. And that's completely new. For no other particle that is so. And moreover, this non-vanishing Higgs field value at the minimum penetrates all the universe, all of space, all of time. Since this symmetry was broken, this non-vanishing Higgs field is there. It's really a medium in the universe, something one would have called an ether 100 years ago. And how can you visualize this spontaneous symmetry breaking? Well, actually, the Higgs, this dependence on the Higgs field, sorry, it's difficult to click, this potential that I'm showing here, it's really more complicated. It's really a potential in more than one dimension. So it's better to imagine this so-called Mexican head potential, which is really this shape, symmetric around the vertical axis here. And you see if the Higgs field sits here at the point of zero field value, it's not going to be stable because it can roll down this potential. In which direction it rolls down is completely random. It's like you take a pin on a table and you let it fall. You cannot control in which direction it falls. If you try to put it absolutely vertical, it will still fall in a random direction. It's so also with the Higgs value. In this spontaneous symmetry breaking, this point is completely symmetric with respect to all direction. Once it rolls down, it breaks this symmetry. That's what we call symmetry breaking. Then it's no longer symmetric. And now this Higgs field is everywhere, and the other particles, they move in this Higgs field. And they feel some resistance. They feel a drag force, and the drag force turns out to be proportional to the acceleration of the particles. And the constant of proportionality depends on the particle that you consider. So it's specific for each particle, and that is what we call mass. Okay? It's just a measurement for how strongly particles are slowed down by the presence of this Higgs field. And even more, if we have a constant medium everywhere in space, any medium can be excited to do oscillations. Think of a water surface. Yeah? You throw something in, you get waves that spread out, or the air in this room when we talk, the air vibrates. And in quantum theory, vibrations, again, correspond to the exchange of particles. And in the same sense that the photon is the carrier of this laser light, the Higgs particle is the carrier of the oscillations of the Higgs medium. So that's what the Higgs particle does. It gives mass to all the other particles, and it is the particle that mediates these vibrations in the Higgs medium. So it's really a very special particle. After the symmetry is broken, the Higgs field lives in this minimum that it can oscillate about. And in the minimum, it's described by this potential, which depends on the Higgs mass, the value of the Higgs field everywhere in the universe, and in addition, a constant lambda. And it has 4 terms. Now, in the standard model, this lambda is not a free parameter. It's actually given by the Higgs mass divided by the so-called vacuum expectation value of the field everywhere in the universe. And the value of lambda is about 0.13. But measuring the shape of this potential is an important goal for future high-energy physics. In fact, this is one of the main motivations to build more powerful accelerators, is to measure the shape of this potential. Why? Because this Higgs potential we have seen in other areas of physics before. Whenever people find spontaneous symmetry breaking, this potential appears. For instance, in the theory of superconductivity. And in all other cases, we found a deeper reason for why this potential is there. In the case of superconductivity, it's the so-called BCS theory of superconductivity, which explains why this potential exists. And it also describes small corrections to this potential, quantum corrections, which should exist. Now, in the standard model, we would love to have this. We would love to have a deeper understanding for how this potential arises. And we would also like to see quantum corrections to this potential. And again, that's the reason why measuring the Higgs potential is an important goal for the future. The Higgs potential is also relevant in the early universe because when you switch on temperature, when you take today, our universe is extremely cold, almost at zero temperature. But if you go back in the past, the universe was a pretty hot place. And as a function of temperature, you see that the shape of this potential changes. And at a certain point, it really develops a minimum at the origin. And then this Higgs medium disappears. And then all the particles become massless. But actually, it was the opposite. In the distant past, all particles were massless. Then the universe cooled down, the symmetry was broken, and the particles acquired their mass. And this is an example how quantum effects actually can change the shape of this potential, and we would like to understand this better. Okay, so I want to summarize the standard model. What have we learned from the standard model? Well, we learned that fundamental forces are derived from symmetries. I have not shown you that, but I just stated here. The symmetry is called gauge invariance. If you write down the symmetries, the forces follow mathematically. We learned that mass is generated by spontaneous symmetry breaking. We learned there are 3 fermion generations. There's actually a reason for that. If it wasn't like that, matter and antimatter would behave identically. But we know, looking at the universe, that actually matter, there's much more matter than antimatter in the universe. So 3 fermion generations is one of the criteria that allows us to get that. And familiar matter consists of only 3 elementary particles, electron, up quark, and down quark, which is a huge reduction compared to your periodic table of the chemical elements, okay? Of chemistry is described by these 3 particles. Now, at a fundamental level, more profoundly, the standard model, and in particular relativity and quantum mechanics, which are its building blocks, has revolutionized our notions of space and time, the famous relativity of space and time. I show this picture by Salvador Dali, The Persistence of Memory. I think this was the title slide of Michelangelo Mangano's lectures half a year ago. And Dali apparently dreamt about, in a dream, he reflected about Einstein's discovery of the relativity of time and came up with these harmonic clocks, which show different times and also are curved because space can be curved. But not only that, also our notion of locality. Normally we thought that in physics, if something happens, it happens because of a reason at that point in time. But in quantum mechanics, there's this spooky phenomenon of entanglement. You can have 2 particles, for instance, 2 electrons, which are entangled, which means that even if you take these particles arbitrarily far apart, there is something connecting them in the sense that if you perform a measurement on one particle, instantaneously something happens to the other particle. And people think maybe there is a wormhole connecting these states, which does that entanglement. Is something that we really don't understand at a more fundamental level, but it's the most bizarre thing about quantum mechanics. And then also we learned that nature is not deterministic, because quantum mechanics is not deterministic. It has a stochastic element to it. We can predict probabilities for things to happen, but not what will actually happen. So quite radical notions of elementary things which have been changed. We also know, that's also very profound, that mass, charge, and angular momentum are not bulk properties. Normally you think, if I have a large object and it has a certain density, it has a certain mass. And if I make the object twice as big, it has twice the mass. But actually, mass is a property of a point-like object in the standard model. Charge is a property of a point-like object. And even angular momentum, the so-called spin, is a property of point-like objects. And that's all we can say about these point-like objects. So in the standard model, if you look more in detail, they give you 3 numbers, the mass, the charge, and the spin, and that's it. That describes the particle entirely. It's very interesting that the most fundamental objects in gravity, which are black holes, are fully described by giving their mass, charge, and angular momentum as well. So somehow nature at the most basic level cares about these 3 properties of things. Standard model also challenges our understanding of reality, and I think Michelangelo also talked about this point. And the reason is that most particles in the standard model are unstable. I already showed you all the heavy ones decay. They decay incredibly fast. So for instance, a top quark, which is the heaviest standard model particle, traveling at near light speed, decays after a distance that is only 1/10 of the size of an atomic nucleus of a proton. So what does it mean to say that we have discovered a particle if after it was born, it decays after 10 to the minus 25 seconds? Or in the case of the Higgs boson, after 10 to the minus 22 seconds. Okay, these things live for a fraction of the size of an atom. Well, as physicists, we consider a resonance to be a particle if its width is much smaller than its mass, which is actually true for all these extremely short-lived states. So for instance, the top quark width compared to the mass is less than 1%. For the Higgs boson is less than 3 times 10 to the minus 6. So these things are very narrow resonances, and therefore we describe them particles, but from a mathematical point of view, they're not what we would call good asymptotic states of the scattering matrix. So they're really resonances, these states, not particles, but we can nevertheless them do very, very accurate predictions for them. And I want to show you one example here. This is actually a real event display from the Atlas experiment of an event where 2 top quarks were created, but these top quarks themselves cannot be observed. I just told you they live for a split of a second. What can be observed is their decay products. And what you see here is one of the top decays into a charged lepton, a muon, which you see as this blue line. The color is not easily visible. So this muon is easily reconstructed experimentally. There's a neutrino which is invisible, and that's shown by the dashed line. You can say, well, how do you illustrate something that you can't measure? The reason is we have momentum and energy conservation. So if we measure everything else, this invisible particle, we can reconstruct its momentum. And that's shown by the dashed line. And then the third thing in this decay is a B quark. But the B quark itself is very short-lived. So it actually decays to a spray of particles which builds a jet. And that's what is shown by this yellow cone. So the blue line, the white dashed line, and this jet is the first top decay. And you reconstruct the top by measuring the properties of these lines. And the other top quark decays into 3 quarks, which build 3 jets. And you see them here, 1, 2, 3. This is reconstructed to be the second top quark. So you see, it's very, very indirect. you see the decay products of the decay products of these top quarks, but using energy momentum conservation, you can nevertheless reconstruct that it was two top quarks that decayed here. Now, I told you a lot about the standard model. The most important thing that it actually works. And it works beautifully. As I said, everything we ever measured in the microcosm has been confirmed by the standard model. And this is a beautiful plot from the CMS experiment. This is rates of different production cross sections. So you collide two protons and you produce, for example, a pair of top quarks, or a pair of W bosons, or a Higgs boson, or a Higgs boson plus a Z boson, okay? Many, many, many possibilities. In each case, the colored object is the experimental measurement, and the theory prediction is this, you cannot see it, it's a little brown line here, which is very, very narrow because the calculation is very accurate. And you see that the predictions in all cases agree with the measurements. And the remarkable thing of this plot is that it covers 14 or even 15 orders of magnitude in rate. So 15 orders of magnitude, that's 1,000,000 times a billion. And over this enormous span of rates, the standard model explains all these observations. And I have two more nice applications of the standard model. This is something very dear to my heart, but I will not explain you the details. Let me just say that the fact that the Higgs boson couples to fermions of different generations also leads to the possibility of generation changing interactions. And those are described by the elements of a matrix, which we call V, the Kabibo-Kobayashi-Maskawa matrix. And this matrix is unitary, which means that it satisfies certain equations. These are complex numbers satisfying certain equations, which can be drawn as a triangle. And this is shown in this figure is different experimental measurements of the length of the sides and the angles of this triangle. Every color is a different experiment. And you see they all come together in this tiny little point here. So there's, all the measurements agree with this triangle having that shape, which is incredibly beautiful confirmation of the standard model. And this is another incredibly beautiful confirmation. This is the most precise, or one of the most precise calculations ever done in physics. Anomalous magnetic moment of the muon. This is something that without quantum mechanics would be 1. In certain units, this G factor would be 1. Relativity and quantum mechanics, it's 2. And then with quantum field theory, it's 2 plus a small correction. So one defines a quantity A, which is the difference from 2, defined in this way. And this quantity is very small. Julian Schwinger calculated it in 1948 for the first time. And he got this value, 116 times 10 to the minus 5. So 0.00116, very small number. And the measurement perfectly agreed with this very small number, okay? Not in 1948, later. The measurement became so precise. Later people computed higher order corrections to this prediction and predicted this number, which, as you can see, still agrees beautifully with the measurement. And nowadays, this is the situation. The theory value is this. This is now times 10 to the minus 11. The experimental value is this. Now you see a difference, but the difference you see, these are the errors. The difference is less than what we call a standard deviation. So it's in very good agreement, experiment and theory. And in fact, the difference is 38 times 10 to the minus 11. So that means we predict and measure this quantity with an accuracy of 1 in 10 billion, and they agree. Okay, so that's how accurate one can calculate in the standard model. So now you would say, great, we found it. That's the theory of the world. Well, not quite. The standard model describes very well the microcosmos. but there are both observational things and also theoretical issues that it doesn't explain. Now, the observational things, which are the hard facts, they're all related to astrophysics and cosmology. When we look at the cosmos, we find dark matter. The standard model doesn't contain it. In the cosmos, we find more matter than antimatter to an extent that the standard model cannot explain. There is a small asymmetry, but it's not enough to explain the data. In the cosmos, we see that in the younger cosmic age, the last billion years or so, the universe expands in an accelerated way. That's called dark energy or cosmological constant, and we don't have a way to explain that. In fact, that is a huge problem. It's called the cosmological constant problem. It's the one problem for which there's not really a very good answer. And then also, as I said many times, gravity is not contained in the standard model. The reason being that gravity has not been unified with quantum mechanics. Gravity is still a classical theory. It's general relativity of Einstein. It's probably the most beautiful theory of all, but it's classical, it's not quantum. And this is still an extension of gravity, which we don't know exactly how to do. This is the hard facts. You know, this is not described by the standard model, but the standard model was built for the microcosm. Nothing here has to do with the microcosm. So you could say it's not so bad, actually. Why would we worry? But there's also theoretical issues that people worry about. Maybe for good reasons, maybe for not so good reasons. So in the standard model, we have the electroweak force. It turns out this electroweak force is still many orders of magnitude stronger than gravity. And the question is, why is that? That's called the hierarchy problem. When we look at the masses of the fermions and these mixing angles that I showed you earlier, we see drastic patterns. The masses are very different in exponential ways. What explains that? That's the flavor problem. What explains the smallest of the electric dipole moment of the neutron? I haven't talked about this. In the standard model, this thing could in principle be measurable, but all the measurements found zero. That's the strong CP problem. And then the question, can we at all explain the constants of nature and the symmetries of the standard model? So why is the electron as heavy as it is, or the top quark as heavy as it is? Is there an explanation? Maybe the answer is no. Maybe think, is there an explanation that if you look at the sky, the moon is almost exactly as big as the sun? No, it's pure accident, okay? The moon is tiny compared to the sun, but it happens to be so close to us that it looks for us to have the same size as the sun. So sometimes things are just the way they are, but we don't know. Maybe there's an underlying theory that explains all the constants in the standard model, maybe not. So these are theoretical questions. We don't know how seriously to take them, okay? These ones are observations. We must take them seriously. So they're something beyond the standard model. And of course, as theorists, we have many ideas what it could be, and there are solutions to almost all the problems that I wrote down. We just don't know if they are true or false. Now, what does the data say? So there are direct searches for physics beyond the standard model, which is called new physics, at what's called the energy frontier, the highest energies available. And at the LHC, one just looks for new particles predicted by various scenarios of physics beyond the standard model, and one didn't find anything. And this is the exclusion regions. This is what we can exclude. So for instance, if there are new heavy force particles, we haven't found them, so we know their mass must be heavier than 3,000 times the proton mass. Now remember, the Higgs boson is 125 times the proton mass, so more or less a factor 10 heavier than that is excluded, okay? And in many other scenarios, similar exclusion plots. We can also look in an indirect way for new physics by just looking at low energy measurements, but looking for small quantum corrections from heavy particles to low energy measurements. That's what we call indirect searches for new physics. That's the luminosity frontier. You need very high intensity to do these searches. is excluded there. And this is 1,000 times the proton mass. This is 10,000 times the proton mass. So again, we more or less excluded 10 times the scale of the standard model. Now, is it a problem that in the 12 years after the Higgs discovery, the LHC has not found any new particle up to 10 times the scale of the standard model? Many physicists would tell you, yes, this is a catastrophe. It's the end of physics. We'll never find anything anymore. This is really nonsense. Sorry to be so blunt. It took 50 years to find the Higgs boson after it was predicted. If you go back to the last classical theory, electromagnetism, Maxwell's equation, 1860, okay? It took 40 years until relativity was invented. It took 60 years until quantum mechanics was invented. And it took 80 years until quantum field theory, the basis of the standard model, was invented. So, sometimes we just need to be patient. And I want to give you, maybe I skipped this. Sometimes we just need to be patient, okay? But when we need to be patient, it's important that we look with all tools we have available to us. And so in the last part of the talk, I want to talk about enlarging the toolbox. Now, of course, you can do what we have always done, namely, you build a collider, you do the physics that you can do there, and then you build a bigger collider, a stronger microscope, okay? And there are indeed plans for that. Here's the LHC on the Swiss-French border. Here's the Lake of Geneva. This is the so-called future circular collider planned by CERN, which will have a 90-kilometer circumference. So it's much bigger than this, actually 3.5 times bigger, okay? This is the future machine that maybe CERN will build. It looks like this is the first priority for CERN. And in this machine, you could collide electrons. You could also collide protons. So there's 2 different versions of running this machine. Before we get there, this is going to take at least 20 years to build. We have the so-called high luminosity run of the LHC. So the LHC has been upgraded to higher intensity. That is approved. And we have the electron-ion collider at Brookhaven in the United States is also approved. We have plans for a machine like this in China, CEPC. And we have alternative plans instead of building circular colliders to build linear colliders, also at CERN and elsewhere. And we have plans to build a muon collider in the United States. So you see, there's many things. Not all of them will happen. We're happy if one of them happens, because they're all very expensive, of course, and they need really large international collaborations. But we can also do other things, okay? A particular exciting one between the microcosmos of quarks and the macrocosmos of the whole universe. And the connection has to do with the early universe, the very, very early universe. So, as you all know, the universe was born in a what we call the Big Bang, the singularity, the origin, and then it expanded. And it was very, very hot in the beginning, and as it expanded, it cooled down like a hot gas in a pot. If you let free, it cools down. And, we not only have E equals mc squared from Einstein, we also have energy is equal to a constant times temperature from Boltzmann. So high energy means we can produce large masses, but it also means we have high temperatures. High energy, high temperature, early universe, and the production of heavy masses all goes together. And in this cartoon, you see that very, very early in the universe, right after the Big Bang, you have a plasma of basically all elementary particles that exist. The ones in the standard model, plus everything else. We don't know what the everything else is, but there is an everything else. And it was produced in this very early phase. And then as the universe cools down, this plasma cools down, eventually atoms form, eventually electrons and nuclei combine to neutral hydrogen, and then the universe is transparent. And actually that happened 300,000 years after the Big Bang. And at that point, light was emitted, which we can still measure today. That's the first picture we have from the early universe. And then as the universe cooled down, galaxies form. And here we are now 13.8 billion years after the Big Bang. It's remarkable that, whatever was produced in this early universe doesn't exist nowadays. All the heavy particles have decayed. But if we do our particle collisions, we can reproduce these particles, which is a mind-boggling fact that somehow this is not forgotten. The equations of the Standard Model, the equations of the Standard Model plus whatever is beyond, know about everything that ever happened before in the universe. And there's this beautiful quote from Stephen Hawking: what is it that breathes fire into the equation and makes a universe for them to describe? It's shocking, right? You have an equation, the Lagrangian of the Standard Model, and somehow it's not a mathematical structure, it's a real thing. It's a universe that actually plays the tunes of these equations. And we can recreate in colliders these conditions of the early universe. But we should call it a little bang, not a big bang. We are not creating new universes. We are just trying to reproduce with high energies the conditions that existed in the very early universe. Here's the same plot, but in maybe did I lose my microphone? Oh, I lost my microphone. That's why I cannot hear my voice. So here again, you see the 380,000 years. This is when the universe became transparent, and we can see the light from that epoch. After 3 minutes after the Big Bang, actually, nuclear fusion started. So the first elements, hydrogen, helium, lithium, were produced. Protons formed after 1/1,000,000th of a second after the Big Bang. And actually, particle physics, as we know it now, holds all the way to this incredibly small time, the -32 seconds after the Big Bang. Now, you could say, who on earth cares what happened 10 to the -32 seconds after the Big Bang? And that's a good statement, except we learn in physics that we should not be afraid of small numbers. In quantum mechanics, the fundamental quantity is Planck's constant, h bar. And this h bar, if you express it in the units familiar to us, meters and seconds, is an incredibly small number, as small as this thing. Also, general relativity, if you convert it to a time scale, the so-called Planck time, it points to that scale. So actually, this is the scale of quantum physics and relativity. And we would love what happened before, the so-called period of inflation, because we want to unify quantum mechanics and relativity, and the clue could be there in this period. Okay, so this is why physicists actually care a lot. If you don't care about this, you can say that all problems are solved, because from here on, we completely understand what's going on. Be a little bit brief now on this. So looking at this light that was emitted 380,000 years after the Big Bang, we see the so-called cosmic microwave background. This is a picture of the entire universe. So what you do is you look out in any direction of the sky and you plot it like in the old days when I was at school. You got these maps of the whole Earth on a sheet of paper, and it looked like this. Okay, that's what's called a stereographic projection. So this is a stereographic projection of any point in the sky, and you measure the temperature. Am I losing the mic? No. The universe is called 2.7 degrees Kelvin, minus 170 degrees Celsius, very cold. You measure the temperature and you see there are differences between blue and red, but the differences are tiny, 100,000ths of a degree, very, very small, but we can measure them very accurately. And interestingly, this spectrum of temperature fluctuations tells us a huge amount of information about the universe. What you do is you do a Fourier transformation of the spectrum. You find nice peak and dip structure. It's like when you measure the frequencies of a string on a guitar or a piano, you get the modes that correspond to the different tones. That's the music of the universe, if you like. And from analyzing this spectrum, you see here the measurements are the data, and the solid curve is the cosmological standard model fitted to the data just in terms of 5 parameters. And from that, you learn that the universe is largely made. This little slice here is the matter we know in the standard model, 4.6%. Then there's dark matter, 23%. And then there's something called dark energy, which we have no clue what it is. That's 72%. So, I told you before, the standard model describes everything in the microcosm, but the universe as a whole doesn't care. It knows other forms of matter and other forms of energy, which we don't yet. Okay, and actually the case for dark matter is very, very strong. It does not only come from here, it also comes from galaxy rotation, lensing, large-scale structure formation. I have no time to talk about them, but we really are sure there's a lot of dark matter in the universe, and we would like to know what it is. And in the last 5 or 10 minutes, if I may, I will talk a little bit about dark matter. That's probably the biggest challenge one of the biggest challenges of fundamental physics at the moment. And it's looking for the needle in a haystack, because really we don't know. We know dark matter exists, but that's about it. If you ask what's the mass of dark matter, it could be anywhere from 10 to the minus 22 electron volt. That's, if I convert this to the mass of the proton, that's 1 times the mass of a proton, up to the Planck scale, or even to black holes 10 times the mass of the sun. If you count the orders of magnitude, this makes 58 orders of magnitude, which means to say we have no clue how heavy dark matter is. It could really be anywhere. It could also be here and there, a combination. I mean, maybe there's different types of dark matter. There's names for all of this. Light dark matter, ultra light dark matter, heavy dark matter, super heavy matter. Okay, but we really don't know. Theorists have many, many models of what dark matter could be, but the question is, how do you test it? And obviously, to test it, we need to leave no stone unturned. We really need to look everywhere. We need to look for black holes, that's gravitational wave physics. We need to look at the heaviest particles, that's collider physics. To look at very light particles, that's low energy physics. We need to look at these super, super, super light particles, that's quantum devices, that are actually quantum technology. This year is the 100th birthday of quantum technology, is used to search for this very, very light dark. I was asked to speak a few minutes about our efforts in Mainz. Mainz, we have a cluster of excellence called Prisma Plus, Fundamental Interactions and Structure of Matter. And in that cluster, we perform a variety of measurements of the dark sector. This is the different research areas of this cluster. This started in 2013 and is now funded until 2032. So you see almost 20 years of science in this cluster of excellence. And I just want to show you what we do in the context of dark matter. This is our activity, and we do dark matter, but dark matter searches, this is what we do. We do direct searches for heavy dark matter particles with the world's most sensitive experiment, xenon nton and dark. This is experiments deep underground, which try to measure dark matter particles when they hit the Earth in cryogenic detectors. One can perform searches for the same dark matter particles at the LHC, interestingly, in the ATLAS experiment. It's complementary. It can go to lower masses than these searches. We also do small-scale experiments in-house on our campus to look for mediators to the dark sector. So There's the standard model. There is a dark sector which we don't know. It contains the dark matter. It might contain new forces, dark forces. It might contain structures like dark atoms. We have no idea. You know, dark matter could also form atoms. And there must be a way, or hopefully there is a way connecting the two sectors. We know that gravity connects the two sectors. We hope there are other mediators connecting the two sectors. So we look for vector and scalar mediators connecting to the dark sector. And we also look for light dark matter particles. And we all do that with a new accelerator that we are building in Mainz, the so-called MESA accelerator. And then also using quantum devices and atomic physics tools, we look for these ultra-light dark matter all the way to the left on the mass scale that I showed you earlier. And we do theoretical work on dark matter models and the phenomenology of how the experiments relate to the theory that is behind it. So, I'm not saying we're the world leading institution in that physics. We are one of many, but it's important that one covers different aspects of the dark matter problem because, it's such a problem. Now, I think I come to an end probably, so I will not show you the details. I have a movie here of the accelerator which we are building. Just to give you an impression, what can you do with a few million euros? I should say by now a few 10 million euros, but not billions, right? So this is an energy recovering superconducting electron accelerator. The scale is about 30 meters here, where you use very low energy compared on LHC standards, but extremely high luminosity. We are talking about 10 to the 34 electrons on target for some of the experiments which we are planning. There's 3 experiments here. They're cutting edge technology. For instance, one of the experiments has a hydrogen gas jet target in order to not have any material surrounding the target, in order to have a particularly clean measurement. And energy recovery means that when you accelerate the particles, then you let them interact. But the many, many particles that don't interact, you send them backwards through the accelerator and extract their energy. So you don't lose that energy, and then you use the energy again for the next acceleration. So it's really a cutting-edge machine. I have a picture here. This was groundbreaking. December 22, you can easily recognize because everyone wears masks. This is the president of the university, the minister of finance of our state, and the minister of science of our state, and the guy responsible for the groundwork. And this is digging the big hole here to put the new accelerator in the context of existing infrastructure, which was a challenge to do. And this was December 2020. November of this year, 25, we hope to have first beams at this MESA accelerator. And what I wanted to show you is how you use that to search for light dark matter and mediator particles. But let me skip this because time is running late. And maybe instead I want to spend 1 minute before I conclude to talk about fundamental physics and society, because this physics that I described here is very expensive. It also employs a lot of people. So the expense is not wasted money. It goes to companies building this infrastructure and the salaries of scientists working with these machines. Nevertheless, one should explain why it's useful for countries to engage in that research. And I should give credits here to Mark Thompson, who is the next Director General of CERN starting in January. And he gave this similar arguments at the Lepton Photon Symposium earlier this year. So first of all, of course, one should say that there is a deep cultural value in trying to understand the universe. As long as humans exist, they have been thinking about how things work, how the stars move, later how the solar system works, etc. So this is something that makes us human in some sense. in where nations can come together behind a common goal, even nations that are politically not in good terms with each other, work together on science goals. And CERN, in particular, can look back at over 70 years of international collaboration across Europe and the world. The first time I was at CERN, I was engaged in an experiment, actually, even though I'm a theorist now. And in the experiment, Russian and Soviet Union scientists were working hand in hand in the middle of the Cold War, basically, where politically there was no way for the two countries to engage with each other. But there's also an economic benefit. So you could ask, when we invest these huge sums of money, what do we get back? And economic benefit is in innovation and technology, high-end training of all the young people that work in this field, and of course, inspiring the next generation. So let me give you a couple of examples. And that one you probably know. That's GPS. You probably heard that GPS, accurate GPS, needs to know about general relativity. If you wouldn't know that, your car would not, you would not end up in the street you want to find. It's a big effect. I mean, you would be wrong by hundreds of meters, not just by millimeters. So this is, in a way, a byproduct of general relativity 1 century after its discovery. Einstein did not know about GPS, had no clue. Nobody had a clue whether relativity would ever be relevant for technology, but it is here. In fact, major discoveries in basic science are often the result of new capabilities in technology. Often you need new technology. When the LHC was approved, the technology for the magnets and also for the computing was not in place. People knew it would take 20 years to build it, so they said, okay, let's build it, and in 20 years we will have the computing resources, because you could extrapolate how those resources improved. But it was really pushing technology. And the difference to applied research is that here, the technological development is driven by the scientific need. So people are willing to spend all their intelligence, all their effort over years, over whole careers, to make this technology a reality if it's needed for their scientific purpose. And it's the last slide. Disruptive technologies, of course, have the largest long-term impact. The World Wide Web famously was invented at CERN simply for sharing information and data among collaborations. And it was developed as an open tool to the whole world. It was not a company trying to make money out of that. It was developed as an open tool that we all use nowadays. Particle accelerators are used for cancer treatment, different types of treatments. Synchrotron light sources, all these are accelerators that we need for particle physics. Now, of course, our biggest accelerators are bigger than that, but those were the accelerators 20, 30 years ago, are essential for structural biology, materials design, drug design, and discovery. Here's a beautiful example. The development of Atlas silicon sensors needed radiation-hard material, the same material that was used by Richard Henderson, who won the 2017 Nobel Prize in Chemistry, for developing what's called cryo-electron microscopy. That's a microscopy that you can look to actually see biomolecules in motion. And so this revolution in structural biology, which led to the Nobel Prize, came from technological development in particle physics. So we should not forget that. We have very, very good reasons to justify the science we do. Human curiosity is a good motivator, but technology is certainly also a very good reason. And I wish to stop here. I think understanding the laws of nature is a grand challenge to humanity. I don't think this is an overstatement. I think this is a grand challenge to all of us. They're big questions that will keep us busy for many years to come. The strategy should be to be as complementary as possible. I don't like when people say, fund my experiment, this is the best, don't fund everything else. We need the high energy machines, which are long-term endeavors, very costly. we need the luminosity frontier, but also the low energy frontier, hadron physics, nuclear physics, they're all still important in this business. And the cosmic frontier, where gravitational waves is a new tool which will lead to new experiments in coming decades. I think we learned a lot as humans since we think about these questions, but there's still a lot more to learn. And I invite all of you, in particular the young people, to take this challenge and make your contribution to this field. Thank you very much for staying here and for listening to this lecture. Thank you.
So thank you, Professor Neubert. That was really a very captivating talk. We now have time for some questions. Please raise your hands and our volunteers will reach to your place.
Hello. So I observe a large discrepancy in the magnetic moment of one of the particles, I think muon, which you have calculated. So when you put in relativity, so the magnetic moment is increasing, right? So is it just variation of the mass, or what is it that causing?
No, this discovered by Dirac actually in the mid last century, and this is a relativistic effect.
Right.
It's not a correction to something. It's simply in a relativistic theory. It's simply 2 instead of 1.
Right.
And then the small deviations on top of that are what we call quantum field theory. That's the fact that what we believe is empty space is not really empty. There are quantum fluctuations, and they have an effect on any particle moving through empty space, also the muon. And that's this tiny correction. You know, the 116 times 10 to the minus 5 that comes from these effects. And then the remaining digits, it's by computing these quantum effects more and more accurate.
So when you put in relativity, the value almost doubles, right? So that's what you...
the value doubled from classical electromagnetism to the Dirac relativistic electromagnetism.
Okay.
That's the factor of 2, and the rest is vacuum corrections from quantum physics.
So another very simple question, like layman question to that level. So when we detect these events of particles, which is like 10 power minus 21 seconds lifetime, so how many such events are typically detected, and is there a number?
Okay. It depends on the particle, but nowadays,
for example, Higgs boson.
the Higgs boson, I don't know the exact number, but I think it should be between 100,000 and 1 million probably produced at the LHC. You have to see that every second billions of events happen at the LHC, and the art is to find the ones that produce something interesting. 99.99999% of the events are completely boring. The protons always miss each other, or they interact, but nothing exciting happens. So you really, that's what we call a trigger. So the experiments, they have triggers that look very quickly at the event within billions or couple of millions of a second.
Right.
Interesting. If not, I don't even record the event. I toss it away and I wait for the next one. And even in that way, there are petabytes of data that need to be recorded, but we try to record the more interesting events.
So my question was really motivated by the stupid thought that, like, suppose we consider like neutrons decaying. You start with a large number, and after half lifetime, there'll be like a half of those number will be remaining. So in the case of gluons, or Higgs bosons, suppose we have a very large number of such particles to start with, and after a macroscopic time scale, some of them, if they are surviving, so what makes them survive? That's a question I have in mind.
Okay, so
thank you.
The last part of the question is difficult because that's quantum mechanics, right? So quantum mechanics tells us if I say a particle has a certain lifetime, it's a statistical statement. It means that after that lifetime, let's say half of the particle on average has decayed. And then if you wait another lifetime, yet half of the particles has decayed, and so on and so forth. So I mentioned that for all these particles of the standard model, the width is very, very small compared to the mass. The width tells you the inverse of the width is the lifetime. Okay, so the lifetime is very small, which really means if you produce a top quark and you wait a second, you can produce a zillion of top quarks, none will be left, because they decay so rapidly, right? Even though it's a statistical process. So we are not measuring the width by producing 1,000 top quarks and measuring when they decay. We measure, as I showed you for the Higgs boson, we measure a resonance curve, we see a peak and a width, and we extract the width from that. It's actually a bit more complicated because there's also experimental resolution effects that need to be unfolded. But the rest is quantum mechanical indeterminism. Right? We cannot, for a given particle, you cannot say how long it lives, but on average, the lifetime gives the average decay length.
Any further questions? There is one there.
It was wonderful listening to you. So my question is not related to particle physics particularly. I wanted to ask you something about the power spectrum you showed of the CMB. In that, I could see that initially so it was very well aligned with the theoretical curve, the experimental one. But initially the error bars were very high for the plateau. I don't know the reason for that.
By initially, you mean the first few points
Yes.
on the plot? Ah, yes.
Yeah, smaller multiple.
Maybe I don't go back there, but because you remember, it was the very left-hand side of the plot, the error bars were large. And that's because we're looking at very large angles now. And there's only, so I mean, if you look at very, very small angles, you can generate a very high statistics, right? Because you can sample many points on the sky. If you look at an angle of 30 degrees, you cannot generate, you know.
Right.
So it's called the cosmic variance. We really have a statistical problem there that we don't see. We don't really see temperature fluctuation on these large scales very well. It's very hard to measure them. And the measurement not in contradiction with the data. You wouldn't be able to see it with the light. But the error bars, unfortunately, are very large. Yeah.
But sir, also initially when the satellites were not, the Planck was not there, we could only get the initial curve, right? So
in the beginning, turns out there's useful information in all of the details of the spectrum, but actually the location of the first two peaks tells you, for instance, the amount of dark matter over ordinary matter. So you're absolutely right that with the more recent satellites like Planck, one can now measure 5 or 6 peaks and all the oscillations between. Originally, one could see the first peak and maybe the second, and then the errors were too large. And there will be future measurements of the CMB. There are many experiments planned, and in particular, what one looks for is not only to see the temperature differences, but also the polarization of the light of the radiation that one measures from these various points. So in this polarization, there is important information. For instance, about the period right after the Big Bang, what we call the inflationary period. So the models of inflation, if you want to really ask what happened in this very, very early stage after the Big Bang, this polarization of the CMB can be very helpful.
So about that, you're talking about the polarization data is also there and temperature. I also saw on the website that there's some temperature and polarization data. Like in the same data, there's PP plots over there. How does that relate?
I'm afraid I didn't catch.
Maybe I'm not able to deliver it properly.
No.
Discuss this later after this talk and take more
Okay,
questions.
sure.
Fine.
Sorry.
My question. Sorry.
It was an acoustic problem. Maybe we can discuss afterwards.
we can take just one more question, and there is one back.
In your talk, you had highlighted how findings proved in fundamental particle physics might be helpful in a broad range of fields. And it is natural to expect findings in other fields to also influence research in fundamental particle physics. In which of the many broad fields do you expect to greatly contribute to fundamental research, not just physics, but in general, in the coming future?
So I should say I'm a theorist, so I really know very little about technological things. But I know, for instance, that recent advances in quantum sensors have really changed the way people think about this dark matter problem. So let's say 10, 15 years ago, people had no idea how to search for dark matter, which is super light. Super means that at a certain point it becomes classical. It doesn't even behave like a particle anymore. It behaves like a wave. Super long wavelengths. And now with the capabilities of quantum sensors, people have ideas of how to search for this type of dark matter. For instance, by looking for things like time variation of constants of nature, etc. So I think this is a beautiful example where technological advances in one field can also have an impact on let's say, particle physics or dark matter searches. I'm sure there are many others where that connection could be made.
Just a small note. Are there any fields which might be unexpected to contribute to fundamental particle physics, but that you might think something might arise? Just.
You said the word unexpected. That's the great thing about physics. No, so unexpected means probably that also I don't expect it. But you know, rarely, but once, many times over a career, something happens that people thought before is impossible. A very beautiful example was the observation of gravitational waves. I didn't have the time to talk about this, but gravitational waves, the one that were observed in the first experiment, corresponded to, so gravitational waves squeeze and shake space, time itself. So the space vibrates, not things in space, which means that length scales change. So if you have a laser interferometer with two laser arms, the one going in this direction and the one going in that direction, if space is expanded and squeezed, they will travel different distances. And the effect corresponds to a tiny, tiny fraction of the size of a proton. And nevertheless, people managed to build devices that were able to detect that measurement. But it took 30 or 40 years to develop the technology. So when people started out, it was completely hopeless. But then you don't give up, and somehow, you know, you're not invited to many conferences because you never see something, but eventually you become successful and you win the Nobel Prize, like in that case. And then everybody talks about gravitational waves. And now, when that happens, people say, oh, well, if we can do it this way, we can also do it other way. So now people use quasars, for instance, to also study gravitational waves, which is a completely different technology. But I think it was driven by the fact that you saw the effect in one technology. It's possible, these things exist, we can study them. And then people get very inventive and come up with new ideas. And that's the great thing about science, that you can, you know, if you try to, whenever people try to predict what happens 10 years from now, just don't listen. It's always better, usually. It's always better. Even at the LHC, when they extrapolate to high luminosity, they tell you what they will be able to do 10 years from now. You look 10 years later, it's much better usually what they can do. Simply because people, if you have 3,000 people working on something, the combined intelligence is enormous, and that shows somehow.
Thank you.
I'm sure there are many more questions and you're invited to discuss afterwards, but let's thanks again, Professor Neubert.
Thank you very, very much for the invitation. Thank you.
Before we disperse, let me just thank some more people who made this public lecture possible. So of course, first thanks goes to Matthias, who gave us this wonderful talk. I'll also thank Dr. Monica Roy, Monica D, and DP's family, who came unfortunately after the lecture started, but of course they are here. The TIFR director, deans, and officials for allowing the use of all the facilities, the auditorium staff and security, also the canteen, and also importantly the PRO office of TIFR and the science communication team. For those who are from outside TIFR, if you do want to be invited for all the future public lectures, you can simply drop an email to scicom@tifr.res.in and your name will be added to the minutes. So thanks all of you for coming. And there is tea and snacks just outside in the auditorium, and we can meet there. Professor Neubert will also be available for some time there to have questions. So let's thank all of you again and Professor Neubert again, and this event will be closed.